learning into 5 different steps and 3 different phases. So first phase being the data pre-processing phase, where we import the data, we clean the data, we split it into training and test set. We learned it the last time when we were feature engineering our data. That means that we were cleaning the data for missing values, and also we were scaling our data, normalizing it, and doing all these things, right? So today we will move on to modeling phase, which is building the model, training the model, and making predictions. Because we have learned how to clean our data, now we will move on to modeling, and then finally we will evaluate our model. That means that we will see how our model is performing by making a performance matrix and a verdict that this is how actually our model is working, right? So let's move ahead in what we learned last time. We learned in data pre-processing, data removal, like if there are some, so pre-processing steps were three pre-processing steps. That means that if we have some rows which have missing data, we can remove those rows. The other way of was which we learned is using statistical imputation. That means that by using mean or median of the data, we are filling up the data, and we can also fill up data using regression, which we have learned in the first masterclass, right? We also learned that we can deal with categorical data, like we had Thailand, Indonesia, China, India as the countries from where the car was being from where the customers of the car were there. So we use one hot encoding to encode this so that it doesn't find pattern in the string that is India, Thailand, Indonesia, and China. That means that we are encoding it into something binary, right? And for the data which is y, which is the predicting variable, we also encode y into yes and no by using binary encoding, which we have learned in our last masterclass, right? And what we will do is we also learned how to feature scale our data. That means that how to normalize it, how to standardize it. We learned it in the last section where we were dividing our data and kind of like categorizing it in the scale of -1 to 1 or -3 to 3 in our case when we were doing standardization, so that we can see the patterns in data, which data is more close to which data and which person is more close to which person, so that our machine learning system can make better predictions by scaling these features in our data. So today's agenda is we are going to learn about multiple linear regression, which we have left in the last section, which we rushed through. Today we are going to have a deeper engagement. Then we will learn about polynomial linear regression, and then we will cover the logistic regression in detail. So let's go back to what we were learning, what we were seeing last time. So we are doing supervised learning. That means that we are training our data, training our machine learning models with the labeled data. So we are doing this case study of this corn farmer, where the corn farmer was producing some corn, and based on the 3 factors that he has, that means that how much area of land that does he have, how much quantity of seed is he sowing, and how much fertilizer is he using. He wants to predict that how much quantity of seed and how much fertilizer should he use, and based on this, how much produce would be there of the corn, right? So what he did is he trained a linear regression model, and the equation of a line will look like b0 plus b1x if it's a linear regression model. But if the farmer has multiple inputs, like the area of land, quantity of seed, and fertilizer, there are 3 different inputs here. So if a farmer has multiple inputs, what will be the regression look like? So the line equation, the linear equation, will change to y hat equals b0 plus b1x1 plus b2x2 plus b3x3. That means that we have now 4 different parameters to find: b0, b1, b2, and b3, right? And we have 3 variables. Let's make this case a little constant. So suppose farmer has this constant area of land where he can sow, and he has only 2 variables that the data depends on. That means that the quantity of seed and the fertilizer used. Okay, so now if we simplify it to 3 dimensions, that means that my corn yield now depends on quantity of seed and how much fertilizer it uses. So the linear regression problem here now turns to multiple linear regression, because now we are finding three different parameters. So the algorithm will become similar, but the visualization will become different. That means that now we are visualizing in 3 dimensions. So in the last masterclass, I told you that if we visualize it as a room, then the seed quantity will be one length of the room, and fertilizer will be the breadth of the room, and corn yield will become the height of the room. So if we realize this graph in a 3 dimension, and all these points, all these data points on which the crop yield is there on the base of how much seed the farmer use and how much fertilizer the farmer use, are suspended in this environment, right? So they are suspended somewhere in middle of the room. Let me just quickly change the quality of my internet to 5G so that I don't have like misconnections. So all right, I'm back. Okay, so now what we need is we so for a linear regression, we were trying to fit in that line which is nearest, which is covering all the data points, right? So we were trying to predict a line which is covering all the data points. Now in 3 dimension, like in multiple linear regression, what will happen is we change this to the line is in 3 dimension becomes a plane, and we are trying to find a plane where most of the points lie, or which is the best fit for all the points that is there, right? So basically what we are doing is we are trying to find this plane from which if I project this, sorry, I need to take a pen. So this distance of all the points from this plane is the minimum. That is what we are minimizing, right? We are minimizing this error. That means that the distance from all these points to the plane is minimum. So that plane will be the best fit for this graph. Now for n variables, the multiple linear regression will look like this. So suppose we have like n inputs on which our data depends on, let's say x1, x2, x3 up to xn. That means that we will now need to find these n number of hyperparameters. And for dimensions greater than 3, the plane will be called a hyperplane. So we cannot visualize the hyperplane for more than 3 dimensions. So it will be something which is called hyperplane, and that would be the best fit for that data. So basically we are trying to find that hyperplane which is the best fit of the data, right? And we're trying to find these variables b0, b1, b2 up to bn so that we can best estimate our data. And these hyperparameters b0, b1, b2, and bn determine which variable our output depends more. So if b1 value is more, that means that our output depends more on b1, more on x1 variable. If b3 value is more, then that means that our output depends on x3 more. So we can also know which factors our data is depending more on using multiple linear regression. We were solving a real case scenario of a Shark Tank that Shark Tank India is going to host or launch its season 4. And the Shark Tank India is in pursuit of people who can apply to Shark Tank India. So they hire a machine learning engineer. Suppose you are the machine learning engineer and you come in the picture, and Shark Tank India says that we have 50 companies from 3 seasons, season 1, season 2, season 3, which are doing well. Now we need to design a system to select the company of season 4 based on the data of these 50 companies, right? So we train our machine learning model to filter out the applications of participants. That means that we are analyzing the profit that the participant company is making, and we are predicting that profit. And on the base of this profit, we are asking them to come to season or not, right? So to make our processes smoother, in Shark Tank season 1, 62,000 people applied, right? So they don't want to make the same mistake that so many people apply, and they just want now the people who are the winners, or who are the kind of like profitable businesses in season 1, season 2, and season 3, analyze their trends and find similar businesses, so that they don't have to like invest in a company which is not profitable. So you come in the picture, they give you a data. The data looks like this. The data has these four columns. So the R&D that the company does spends the company spends on research and development, how much the company spends on administration, how much the company spends on marketing, and how much profit is the company generating. So this is the 50 data of 50 companies. So whenever we input the research and development spent, administration spent, marketing spent, we will be able to analyze how much profit that company is generating. All right. So it's a multiple linear regression problem where there are three inputs: the research and development budget, the administrator budget, and the marketing budget, and also the season. So this is not the state. This should be the season. So in the data, I have solved this. So the season 1, season 2, or season 3, which season that company is featured. So according to the four inputs, how much the profit will be there. If the company is profitable, only that company will be called. So quickly get your data sets here. So your data and templates will be here. You can scan this code or go to this code to get your data and template. So I will paste this code on the chat box so that you can go to this code from the chat box. I will just quickly copy this from my slides and paste it on the chat box. Just a minute. All right, so the code is there on the chat box. You have to go to the code. So once you open the code, sorry, the link is there, the QR code link. Once you open the link, you will be here in this data sets folder. And from here, you can go to linear regression. And in linear regression, the data set is successful startups.csv. So you have to download this successful starters.csv file. So you go here and download it from here. And you also open this multiple linear regression template. So you double click on this and that template will open in your Google Colab. Okay, so you will see something like this. I think I'm sharing the right screen now. Yeah. So you will see a drive link like this, and you will be able to download the data from here. I will also upload, the link is working. The link will work after 3, 2, 1. So if you click on the link, I'm also going through the same link. So you will be reaching this folder. This looks like this. Okay, I think that it is stopping, like it's not working. So I will share this link. Let me just share the link of the folder itself. So linear regression. And share, copy link. All right. I think I'll just copy the link from here. And I'll paste it in the chat box. So if the above link is not working, I'm sure that this link will work to the Google Drive. So you can just click on this and go to the Google Drive, which is the linear regression file. So here you can download this successful startups.csv. For those who are not downloading, then I will share this file successful startup.csv on the chat itself so that you can download it from the chat also. So successful startups. So I have pasted. I have pasted the file also. So you can download the file from the chat box also. Successful startups.csv, and the file looks like this. Okay. Let me just quickly share how my file looks like, and it looks like this. All right. So we have on first column, we have R&D spend, how much the company is spending on research and development. Second column, we have how much the company is spending on administration. Third column, we have how much the company is spending on marketing. Fourth column is which season the company was featured. And fifth column is what profit the company has made. All right. So we are predicting the profit of the company, and the company which have more profit, we will invest in those companies, right? So let's quickly come back to the coding part. You will be having this linear regression. So I'm sharing, let me share the right, yeah. So in this, you select the template multiple linear regression and open that template, and the multiple linear regression template will be opened, okay? So this is the template that we have. I think I changed. I changed this last time. I think I just worked on this template only. So I'm quickly deleting all the columns. Or let's delete all the columns so that we can start from the scratch. All right. So you'll begin with importing the library. So what you need to do is you need to go to File. You need to, I'm just saving this. So you need to save a copy in Drive, and your template, you're not able to open the template. So I will just share the template also. So the link of the template is in the chat. You can also use the chat box to go to the template link. So you just click on this collab link and you will be seeing this template. Okay. So quickly type in done or yes if you have downloaded the data and are in the template. Thank you so much, Manaswini, Shubham, Rania, Leela. Thank you so much, Aryan, Dushyant, Manish. Thank you so much, Hema, Ashwin, for sending me done. Thank you so much. I am really, really grateful to the people who are pasting done and yes in the chat box so that we can paste this lecture and finish this lecture on time, right? So let's start coding. Importing the library is the first step. You already know that. So let's start coding. So we will import the first library. So you need to make a copy of this. So go to File, save a copy in Drive. And once you create a copy of this template, then rename this template by renaming this copy by your name. So Amit template multiple linear regression. This is my case. You can rename it according to your name, right? So let's start coding. So let's import the first library. Import numpy as np, right? The first library. Why we need that? To work with arrays, right? So to work with arrays. And we will import the other library, which is the pandas as pd. And why we do that? Because to work with data set, right? And then we import the third library, which is matplotlib. And from there, we will import the pyplot library, and we import this as plt. This is to visualize the data, okay? So if you have imported this, then run this code, and it will connect to the runtime environment. once it connects to the runtime environment, it will run, right? So it has connected and it has run, it has executed the code. So the second thing that we will do is now we will import the data set. The data set we already have, the successful startups file. So first we will do is we will import that file. We will upload that file to the runtime environment. That means that we will click on this folder. We'll go to this upload option. And from there, where you have downloaded the successful startups file, we will go there and where is it? Successful startups. Search. All right, so let me just upload this only successful startups. And because my file has 1 in it, because I downloaded it again, so I will just rename it to match your file name, which will look like this, successful startups.csv, right? Now we will import the data set and the steps are same. So we will make a variable data set and we will use pandas library and we will use this read CSV function and we will read this file successful startups.csv, right? And then we will locate our independent variable, which is x. X is data set dot ilog, which is the location of where our x is. So for all the rows, and we will see what columns do we want to include. So we will include all the columns up to the last column. So except the last column, which is what we need to predict, we will upload all the columns from column 0 to column 3. So what we will do is, we will upload from column 0, which we will keep as it is, and up to -1. So -1 is the last column, and we will take all the values of the columns, right? And we also will encode our dependent variable, which is dataset.ilog, and we take all the x values, all the row values, and the columns are only the -1. That is the last column, and we take values of all of this, right? So we import the data set, we make a variable data set, and we encode our independent and dependent variable, right? So in my independent variable, X, I have all these 4 columns. So I will show how the data looks like. Share this, all these 4 columns in my input, and this is my output, right? Okay, so once we are done importing the data set and importing the libraries, please type in done or yes in the chat box if we have imported the libraries and data set. Thank you so much, Akshay, Hemant, Rakshit. Thank you so much, Chitransh, Taranveer, Utsav. Thank you so much. You are setting up a pace for the masterclass. I will move ahead with encoding categorical data, right? So now what we have done is we have imported the libraries, imported the data set. Now we need to encode the categorical data. That means that we have only one categorical data with us, right? And that categorical data is in column 3, right? So if we see here, our categorical data is season 1, season 2, and season 3. I don't want machine learning to learn any patterns from this. So I will encode it as 001, 010, and 100. So I need to encode this third column. So what we will do is we have already learned how to encode the data. We will go back to our template of data cleaning. So I go home and I see the data pre-processing template. And I have already done data pre-processing. In the last masterclass we did. So you will also find this data pre-processing. Sorry, not the template, but it should be with my name. Let me just search Amit data pre-processing. It is here. And you also go back to your file and you go to this encoding the categorical data, right? So encoding the categorical data, you are going to just copy this code from here. So from scikit-learn, Sorry, I think I am showing the Excel sheet, right? So let's encode the categorical data. So we from scikit-learn import the column transformer, and we make a object of column transformer, which we call CT, and we'll just copy it from here. We will also import one hot encoder from scikit-learn. So you have done this in the last masterclass, and we are not going to waste time in like typing everything again, which we have already done. And I hope that I am sharing the right screen. So column transformer, and I am copying it from here and pasting in the code here. And I'm just changing this. So instead of zeroth column, I have to transform the third column, right? So my data set was in the third column, right? So I had to transform the third column. That's why I will transform the third column here. Okay. Remainder of the columns, I will just pass through. And final is I will make my independent variable transform by transforming the X. Okay, so I will use this fit transform method from column transformer, and I will change it into an NP array to transform my X. So if I run this code, I will see that my categorical variable is now encoded. So I will just print that, print X, and I will see that my categorical data is now transformed. So 100 for season 1, 010 for season 2, 001 for season 3. All right, so quickly do that. I will wait for the next 3 minutes. All of you, sorry, not 3 minutes, 2 minutes for you to get here. If you are done, then paste and type done or yes in your chat box. All right, so you just need to go to your data preprocessing template, copy this encoding the independent variable part from there, and then paste it here, and you will see that your data is encoded. Okay. Thank you so much, those who are saying done or yes in the chat box. You're doing me a favor by keeping the pace tight. So today we are moving at a very, very healthy pace. We will be able to finish our class on time today. All right, so once we have encoded the categorical data, we will move on to our next step. Our next step is splitting the data set into training and test set, right? We have done that previously also. So we are going to split it, the data set into training and test set. Again, we will go to this amazing library called scikit-learn. And from there, we will see how we can train, test, and split our data. And we will see that you will find it here. And the library for that is model selection, right? So we will copy this from here and paste it here from scikit-learn.model selection. We are including this train test split. Now we have done it multiple times. So X train, X test, Y train, Y test. So we are making these 4 variables, our training set in X and training set in Y, and we are using this train test split method which takes an argument my X and Y, and what is the test size? So test size is 0.2. That means that 20% of the data I am keeping for testing, and my random state, which is 0, so that your and my code works. And I will run this code, and I will see that my data is now split into training and test sets. I can just check this by printing X train and printing Y train. Sorry, not this. Y train, and this is Y train, and similarly X test and Y test, right? So now we have split the data set into training and test set. So quickly type in done or yes if you have trained, if you have set the data set. We can change random state. Tushar is asking, can we change random state? It will change accuracy of the model. It might be it won't change the accuracy level to that extent, but your question is valid, because if we randomly are selecting the training set and test set, then there might be a chance that some of the values are not there when you put a random state something different and put a random state something different. So the training set might change because of the randomness, and that might increase or decrease accuracy by a bit, not very much. Okay. All right, so now we have splitted our data into training set and test set. Now we are going to train the multiple linear regression model on the training set. Okay, so for that, what we will do is same thing. What we are going to do is we are going to go to the scikit-learn library again, and from scikit-learn, we will use this linear regression because it's also a linear regression. So Aryan is asking, is it necessary to use random state? No, it is not necessary to use random state. It is just for education purposes, because your data and my data should look similar. Otherwise, you will say that, you know, I am having something different output or something different prediction than you are having. So to keep that similar for training and education purposes, I am keeping this random state same for you and me. Okay, you don't even need to specify the random state in your statement if you are doing machine learning in real life. So from scikit-learn, we are going to type in here linear regression, and in linear regression, we will go to the linear model, and from linear model we have this linear regression method, right? So linear regression class we will import from the linear model. So we'll go back to our code. We will import from scikit-learn dot linear model. Let's see what the class is. I think it's linear model, and from there we have to import this linear regression class. So import linear regression. Okay, and let's make a regressor, which is object of linear regression class. So it will inherit this linear regression class, and it will be an object of the linear regression class, right? And then we will use the fit method to fit this regressor, which will fit this hyperplane in my data. Okay, so we will try to find a hyperplane for the variables, and that will fit all the data in that hyperplane. All right. So we will fit this regressor by using this regressor.fit method, and we'll fit it on X train and correspondingly Y train, right? So our linear regression is successful. From scikit-learn, we have imported this and we have fit this. Now we will predict our test set results to see whether our linear regression model is working fine or not. So basically we have the Y values. I'm sharing this here. Okay, so we have the profit of the companies already with us, right? So what we have done so far is we have taken 80% of our data. Let's say up to here we have taken. Now for the data that we have for the test set, we are going to predict our profit, and we will check whether the prediction is accurate enough near our test set or not. So we have actual data, and now we will predict our test set results, and we will map or match the data, whether it is predicting fine or not. Okay, so this is what we are doing. Now I'll share this. But to do that, what we are going to do is we are going to make a predictor, first of all, a Y thread, and this will predict the test set results. So we use this regressor and we use this predict function to predict my X test results. Okay. So basically what I am doing is I am predicting my X test results. I already have the inputs with me, right? Which are Y test. Y test already is the output according to X test. But I am predicting them on the base of the model that we have made right now. So regressor is the model, so that hyperplane that we have tried to fit, and we are predicting all the values on that hyperplane, and we are checking whether we are predicting correctly or not. Okay. So I am going to set some print options using this numpy dot set print options class, so that I can print these values side by side. Okay, so I'm using this set print options class, so you can also use that. So basically what we do is if I print y predict and y test right now, let me just do that so that you know what I'm doing and why I'm doing that. So let me just print y test, and let me just print y predict. Okay, y pred. So now my y test values are this, and this is my predicted value. This is my actual value. Now I can't compare it row by row, right? So I want to change this print option so that I can have two columns to compare to. Okay, this is only what I am doing now, right now. So I'm using this numpy dot set print options function to print my options, and I want the precision. That means that the decimal point up to 2 decimal points, so that I don't have this long string. Okay, I don't want this long string of decimal, so I need just up to 2 decimal points, because my actual output was also up to 2 decimal points. So I set print options with precision equals 2. Okay, and then I will print this this string, and I will use this np dot concatenate method to join these two numpy arrays. So np dot concatenate, and what I am going to concatenate is y predict, but I'm going to reshape it so that I can reshape it to a column. And how I am reshaping it is up to length of y predict, and sorry, y predict comma 1. I am transforming it into a column, and comma y test dot reshape, and how I am reshaping it up to the length of y test and comma 1. Okay, and I started this here, and I need to add 1 here to print this. So I am concatenating this y predict. I'm reshaping this y predict to fit it in a column, and test set also to fit in a column. And I am transforming everything to look like a column. So if I print this, it will print these two columns side by side. Now I can compare easily, right? So I can compare that for this value, this was the predicted output. So 103015, and my actual output was 103282, which was not very much different, right? For here 13285, this is 144259. Here 13244, it's 1461. 21 for these two values, it's still 1000 rupees, 10,000 rupees less. For this, it is 6,000 rupees less, the profit that we predicted. For this, it is 20,000 rupees less. For this, it is 5,000, 10,000 rupees less. For this, it is 12,000 rupees less. So it's still closer to my data. That means that there is not that much of difference between the predicted output and the actual output. So my my model will work. That means that if I give any values of any of these values, wait, I'll just share the screen. any of the values of research and development, administration, marketing spend, and season, I will be able to calculate how much profit that that company is making. Right. So let me just share the right file. So we see that our model is working fine. Now let's visualize our model to check the accuracy. How much is our how much accurate is our model? All right. So what we will do is we will plot this, and we will plot a scatter plot for y test and y predict, and we will see how y predict is uh, uh, how y predict is changing on the base of how much y test was. Okay, so I'll quickly plot a figure. So let me just share the right screen. Yeah. So PLT is the PLT is how I imported the matplotlib. So PLT dot figure, and figure size is 8,6. So basically I'm creating a grid of 8,6 size to plot this graph. Okay, so there will be eight columns and 6 rows. Sorry, 8 rows and 6 columns. So it's a rectangular graph. So this plt.figure, it makes the figure size for the graph. And then we will plot a scatter plot. So let's plot a scatter plot of y test and y predict, and let's color that to blue. Okay. And transparency will be maintained from alpha. So we will make it 0.7 transparent so that we can see the grid lines also. Okay. So scatter plot, y test and y predict. Basically, we are on the x-axis will be y test, and on the y-axis will be y predict. And we are plotting this scatter plot, which is of the color blue, and transparency of that plot is 0.7. Right. Let's X label will be actual values versus predicted values. Okay, so that's the label of our graph, and Y label is Y label is predicted values. Y label is predicted values, and X label is actual values. This is actually the name of the graphs. This should come in the title. So actual values is here, predicted values, and PLT dot title will be actual values versus predicted values, right? Now I am going to plot a line which is y equals x line, so that I can see how much variance is there. So I'm plotting basically a line which cuts through the graph in center, and I will see how much variance is there in the predicted values as compared to the values. Okay, so for that I needed to plot this from minimum of y test to maximum of y test, and that will be my x, and my y will be same. So minimum of y test to maximum of y test, and both the values are same. That means that it's a straight line, and I color this line as red, and transparency means alpha is 0.7. Okay. Uh, Let me give the line style also. So line style is dotted, is dash dash dash. Okay. Dash, dash. All right. So this is the plot, and if I show this plot, then I run this code and I will see the plot like this. There is an error in line style. I think I have just written lin style, should be line style. And yeah. So this is my graph. I can see how much. So this is how much the variance uh, of my data with respect to the actual prediction. So this line is the actual prediction. That means that y test, this line is what y test is, because here the values are from it, and these are the y prediction results, which are varying from the actual line. Okay, so we can see that it's not that far from the data, because the scale of the data is from 80,000 to 1,80,000. So it's not that far. That means that our model is somewhat perfect, right? So this is just to visualize how much deviation is from my model, right? So quickly do this, how to visualize the result to check the accuracy. Basically, we are plotting this plot to check the variance in the data, and we can do it by plotting x test, y test, and y predict in a scatter plot, and then actual see the deviation from the actual results there. All right. So quickly do this and type in done or yes. Thank you so much. Those who are already saying done, Shubham. Thank you so much, Avni. Thank you so much, Pooja. Why did we write this min y test and max y test? That means that we start from, so basically we are plotting y equal to x graph, but because we are not starting from the origin, it might not go from there. So we start from the minimum of what my y test is. So my minimum of what y test is 77778. So we start from there and we go up to the maximum of my y, which is around here 18 some value, right? So 19150. So we start from here in the graph and we go up to this point. So we correspondingly we plot y equal to x line so that we can see where our test sets lie. So our test sets will lie here on this line. Okay, so for each data point, our test sets will lie here on the data line. And this is the predicted outcome, which is we predicted afterwards. So we can see how much deviance is there. So line is just basically to visualize how much deviance is there. All right. And why did we do it 2 times? Because for one time it is for x. So x ranges from minimum of y to maximum of y, and y ranges from minimum of y to maximum of y. So this is for x, this is for y. Okay, x, y, and color is red, and alpha is 0.7, right? Because plt.plot takes 2 arguments. What is the x label and what is the y? So x and y are same because we are plotting y equal to x graph. That's why we did it like this. Okay. All right, all the errors which the people have, let me just share this. Screen. So first, Janvi is having an error here and could not convert string to float season 3 because you have not converted the categorical variables. So categorical variables are here. So you need to convert the categorical variable using this encoder. And encoder, please use it on third column. Okay, please don't use it on zeroth column. Please use it on third column, because our third column is the categorical data, right? So we have done with multiple linear regression. Multiple linear regression we have done, and so we can design a system where we can take these three values and then can predict the outcome. All right, so we can design any user interface just like we designed last time, where the person is inputting three values and then we are predicting some profit, and on the base of that profit we are categorizing whether we should invest in that company or not. So we are not going to design the input output model for that. That can be designed in any way. So you take input and you define the output for it. Let's move on to our next section, which is this. So some people are having errors. Shubham is asking, can we try predicting the profit of company outside the data set? Yes, that's the use case actually, Shubham. We are predicting the profit of company outside the data set only. That's why we are doing regression, right? Otherwise, we could have just hard coded. So basically, we are trying to make a system where we are designing a system where we can predict the profit of any given company based on the three outputs. Some people are still asking for the last line, so I'll just show you the last line, which is plt.show. Okay, that's the last line. Tushar is having a problem here where here you have not closed the y test. Okay, Tushar, you have to close this here. Y test को close करो and then max of y test. So you have not closed the bracket here. Janvi has sent me the screenshot of one out encoder. Yes, now it is fine. Okay, so you will be able to work on this. But you have to, Janvi, you have to execute the code first. First, execute that code and then execute this. So you'll have to execute this first. Or what you can do is you can go to runtime and you can run all. Okay. All right. So let's move on to the next section, which is polynomial linear regression. Your line is not being shown because of your alpha value. So your alpha value should be 0.7. Okay. All the errors that are there, Tushar, your problem I have solved. You have not closed this. Okay. You have to close this. आपने y test शुरू तो किया, आपने ये close नहीं किया. So if you don't close this, it will not take. Okay. All right. So that one was the other Tushar. Okay. So Tushar Saxena was that error. All right. So let me. Yeah, your line is straight. Why your line is straight is because you have only one value here. Okay. आपने ये सिर्फ एक ही बार लिखा है. So if you just write it for once, you will have a straight line. Okay, Tushar, you have written only for once. All right, so let's move ahead. Now at 6 I will solve all of your doubts. ठीक है, तो अभी अपने doubts अपने पास रखो. 6 p.m. sharp I will start solving your doubts and your errors, so that the people, those who have some commitment where they want to go to some other place after 6, they don't have to wait for the people, those who have errors, right? So let's move on with the session. Even if you have not completed the code, I will just repeat it one more time after 6 so that you can finish your code there. So what if, now let's splitting code. Karthik is asking for the splitting code. You mean train test split? You can check your previous codes from there. You can copy nothing has been changed from there, right? So, all right. So now, what if our data doesn't behave linearly? What if the data behaves like this? Okay, so for a particular type of corn use, the crop yield on the base of fertilizer is not linear. It is somewhat in a curve fashion. Okay, what if it is like this? All right, so now I cannot fit a linear line. So if I fit a linear line, I will miss most of the points, right? So all the points here will be missed. So all these points, so it is not fit, it is fitting only 2 points, and this is not the best fit. So a line cannot be a best fit of this type of data. So how to fit a curve? No matter what kind of line did I draw, like I cannot fit a single line. So I cannot use uh, I cannot use the estimate as a line. So I still need to fit this data with a curve. So how to fit a curve for this line? Okay. What we will do is we will still use linear regression, and not to be confused that because it is not a line that we will not use linear regression. It will still be a linear regression, but how to use linear regression to fit a curve, how to make an equation of a line such that a curve is fit. All right. So this might look ridiculous to you, but we are actually fitting a line, but we are manipulating the input. Basically, we are changing the input to extract to fit a curve in this data. Okay, so basically what we call it feature extraction. So what we will do is the equation of a curve, it looks like y equals some x square, all right, or some x cube, because y equal to x square graph is this. It's non-linear graph, and we need to fit that curve, right? So what we will do is we will change the input. So input is x, and we will extract feature of that input. That means that we will extract the degree of polynomial for each value of x. So for x, suppose any data point, so 20 is the data point. For x equal to 20, we will extract the features as x to the power 0, x to the power 1, and x to the power 2. So basically we are feature engineering our input. So my input x now becomes x to the power 0, x to the power 1, x to the power 2. That means that it becomes a second degree polynomial, and my linear regression equation will become the same. So linear regression equation doesn't change. I only change my x. So that's why it is still called linear regression, because I'm not changing the equation of the line. I'm just changing, I'm extracting more features from my input. So I'm extracting this x1 square, I'm extracting this x1 cube up to x1 to the power n. And that n, up to what degree I will extract the features of my input, will be called the degree of polynomial. And it's a very important hyperparameter. By changing n, we will see our graph, we can fit our graph in a different way. Okay, so by changing n, we can either fit all the points in the graph, or maybe we fit some of the points in the graph, maybe we fit less points in the graph. So by changing n, we will determine how much points or how much my graph is fitting this curve. Okay, so basically what I did is I took the same equation. I took equation of a line, which is y equal to b naught, which is intercept, and plus b1, and I change x. So x as x to the power 1. So x to the power 0, this b naught is b naught x to the power 0, and this is b1 x to the power 1 plus b2 x to the power 2 plus b3 x to the power 3 plus up to so on up to x to the power n. All right. So I extract more features from my data, and by extracting features, I can fit a curve also with linear regression. All right. So the n hyperparameter, so the degree of polynomial n is the parameter whose value we can change in order to fit our model. So if our model is like not fitting like this, so if I change my value of n, I can fit this model by increasing or decreasing my n. So I can extract more features. So if the degree of polynomial is less, let's say y equal to x square, if n equal to 2, then some points might not fit. If the degree of polynomial is very high, then it might fit all the points in this graph. Okay, so sometimes this equation is also not desirable because it will lead to overfitting of our data. That means that our data is being overfit because we are covering all the data points that are there in the training set, and our prediction is more and more relying on the data that we have. It should be able to see the unseen data. That means that it should be generalized enough. So if we overfit our curve like this, that is also not desirable. If we underfit our curve like this, that is also not desirable. So we need to find a sweet spot where we are not either overfitting or not even unfitting. Okay, underfitting. All right, so let's quickly code that. This is the same link. You have to go to the same folder which is there, and here linear model folder, linear regression folder. I will copy this and paste it in the chat box again. Meeting group chat. All right, so please go to this drive link, and there is the corn yield data. So we are going to predict the corn yield, and because our data is now not linear, we will try to fit in the polynomial linear regression from the linear regression class. Okay, so we will download this data set from there, corn yield.csv. So if you have not downloaded it from here, I will paste the file on the chat box. I can paste the file on the chat box, which is cornyield.csv, and it is there on the chat box. You can download it from chat box. Sorry, I just uploaded it for a single person. Okay, Janvi, I will solve your error by the end of this lecture. So you will have to wait for that. Okay. So corn yield, I have the data set I have uploaded. Now you have to open this polynomial regression template. So open this polynomial regression template. The link of the template, again, I am sharing it in the chat box. So you can go to the chat box and check the link of the template also. So the file and the link are from there. Open this link to go to this template of polynomial regression. Okay, so polynomial regression, this is a template, include the libraries, same steps. So we will do this quickly. So you have now known the steps, the first 3 steps, right? So what we will do is we will make a copy of this template, save a copy in your drive, and rename it. Okay, so save a copy in your drive and rename it to your name. So the copy of rename it to your name, which is Amit, right? And now you have done the copy. Now start importing the libraries and importing the data set. So we will not code it again. So let me just do it quickly. Import NumPy as NP, import pandas as PD, import matplotlib.pyplot as plt. Okay, so just run this. In the chat box, please type done or yes if you have if you are at here, that is you have the template and you have the data set. Thank you so much, those who are replying. Thank you so much. Those who have any errors in the previous code, I will solve those errors after 6. So thank you so much for replying done. Inshra is saying that this is not opening on tab. It will open on tab. So if you go to file and save a copy in drive, it will open. Still, I will paste the template link again so that all of you can go to the template. Okay. All right. So we will code the second part also. That means that we are also going to code the importing the data set. So let's first import the data set. So here on this folder, upload this and upload this corn yield file there. Okay, upload the corn yield file because we are using this corn yield data set. Let me quickly show you what the con yield file looks like. Wait. Right screen. I think I'm sharing the right screen, right? So con yield file looks like this. Downloads. And yeah. So I think I'm not sharing the right screen. I'll just okay. So sharing this corn yield file. So this is how the corn yield looks like. So on one hand, we have a fertilizer used, and here is the corn yield, and the data does not behave linearly. So we will do the feature engineering in the data. That means that we will make the data up to a degree of polynomial so that we can fit a regression line like that. Okay. And I'm going to share where we are coding. All right, this you already know. We have imported this data set con yield.csv, and let's create this data set, which is pandas.read CSV, and we are going to read this file, which is con yield, right? And after reading this file, we will encode X, which is data set dot iloc, and from all the columns and to all the rows except the last one, right? So -1, same thing. So I have kept the code constant so that you don't have to change it anytime. You can also copy it from there, or you can copy or type anything with 1. Okay, so -1 and dot values. Okay, so we have X, we have Y. All right. Con yield.csv, sorry, con yield.csv. Okay. Now it executed. All right. So now we will train the linear regression model on the whole data set. And how we will do is we will fit a linear regression model. So what I'm doing is I'm going to compare the linear regression and polynomial regression, and we will see how the features engineering changes. Okay, so first let's do the linear regression and see how the linear regression looks like, and whether if we can fit a linear regression also in this or not. All right, so we will from scikit-learn we will import linear model. We will import this linear regression class. Okay, so what we are doing is we are also plotting linear regression to see whether we can fit a single line in this data, because we don't know whether the graph is polynomially behaving, like it is behaving non-linearly or linearly. So we will train a linear regression model, and we will see whether linear regression is working or not. So we will import this linear regression plus, and I hope that I'm sharing the right screen. And from that linear regression class, we will make a linear regression. So let's call this object linear regression, LIN reg, linear regression, and it will be an object of this linear regression class. Okay, and let's fit this linear regression to our X and Y. Okay, we are not splitting our data set into training and test set right now, because we are not interested in predicting the result. We are just interested in the polynomial regression model. All right, so we are not splitting this data because it's a small data. So I'm not splitting this data set into training and test set. Okay, so I'm working on the whole data right now. This is not the process, but just to teach, I am doing this. Okay, just to tell the difference between linear and polynomial regression. Okay, so I'm fitting this linear regression on X and Y, and let's do that. Okay, so linear regression. Let's now train the polynomial regression model on the whole data set. Okay, so to train the polynomial regression, we will go to scikit-learn, which is our library, and we will search for polynomial features. Okay. So I told you that we are going to feature engineer our or feature extract our input, right? So first we have to extract the polynomial features from the input. For that, polynomial features is the library, and it is a pre-processing stage. So we extract features at pre-processing. So we will see how we can do the polynomial regression. So I will just keep it together, polynomial features, and we will see from where we can extract it, polynomial features, and we can import it from scikit-learn.preprocessing library. So we will go back to our code, and we will type in from sklearn.preprocessing library. We will import this polynomial features class. Okay. Let me check if it is right. Polynomial features. All right. So it takes argument what degree should I assign it to, and interaction, bias, order. It takes different arguments. Right now we are only focused on the degree of the polynomial that we will assign it to. Okay. So polynomial features. So basically what we are doing is, if I share the whole screen again and go back to this slide and I delete everything. So basically we are changing x to n degree polynomial. So x to the power 0, x to the power 1, x to the power 2 to fit in this linear regression line. Okay, so I'm using this library from scikit-learn to extract the polynomial features. So I import this polynomial features class, and I will create a polynomial feature, which is called PF, and it will inherit this polynomial features library class. And the only parameters that I need to specify here, it will show degree, which is 2. Okay, so let's start with degree 2, and degree equals 2. Okay, let's start with degree 2, and we will change this degree to see how changing this parameter will change my output. Okay, so I designed this polynomial feature, and I will make this x. I will make this variable x poly, which will have these polynomial features. Okay, so I will use these polynomial features, and I will fit those polynomial features in this x poly, and I will transform this fit transform x. So I'm changing x to x poly. Okay, so basically I'm transforming x to extract polynomial features of degree 2 from it. All right, so I will also show what that looks like. And then we create a polynomial regression, which we will call polyreg. And this will be a class of a linear regression only, because in reality it is linear regression only, but we are changing the features of x, right? So we are changing the features of x and doing linear regression to obtain this non-linear curve. All right, and I will fit this polynomial regression on x poly. Okay, and y. All right, understood this. So from scikit-learn, we import this polynomial features class. We extracted the polynomial features of degree 2, and we made the polynomial features as x poly, and we transformed the polynomial features of x, and we created a polynomial regression, which is inheriting this linear regression class only, and we are fitting this on our x poly, the features, and y, right? Let me just run this code. All right, so let's visualize how x poly looks like. So if I print x poly, so how it looks like. So it has extracted degree 1, like x to the power 0, which is 1, x to the power 1, which is the x itself, and x to the power 2, which is the square of the input. Okay. So the polynomial features have been extracted like this. Now, let's visualize the linear regression results. Okay, so first let's visualize the linear regression results. We have done linear regression here, and let's see what our results look like. Okay, but before that, quickly do this, that is training the linear regression and training the polynomial regression. Okay, so if you have done training the linear regression and training the polynomial regression, please type in done in the chat box. Thank you so much, Shaq. Thank you so much, Mohit, Tanisha, Aryan, Rakshit, Dushyant. Thank you so much, Hema, Krisi. Thank you so much, Avni. Thank you so much, Hers. All right, so we are setting up a good pace. That means that by 5:35, we will be done with the polynomial regression, and then we will go on to logistic regression. Because we have to cover one more regression in today's class. Okay, which will be classification basically, but we will still call it regression because we will use a logistic function for that. Utkarsh is asking, why did we make polynomial regression? So because polyreg will be linear regression only, but it will fit the x poly, which is the extracted features of x. So linear regression only, but with x poly, that means that extracted features of x to the power of 0, 1, and 2. So basically we are varying x, but by varying x, we are varying the graph. Okay. Linear regression is here. All right. So quickly do that and we will move on to visualization. So linear regression is this. We made a linear regression class, which we will call linreg. So this is the object of linear regression. And we made a polynomial regression, which takes in input as the polynomial features, which we created using this polynomial features class. Okay, and we have created this degree of 2. So if we change this degree, we will see how our graph fits the data. All right, so let's visualize the linear regression results first. So we will start with plotting. So plt.scatter, and we will plot what x train and y train is nothing there. So xy, and color is let's say blue. Okay, scatter plot, and then we will plot the linear regression line. So plt.plot, and this linear regression line, which will be between x and which will be between x and regressor, which is linear regression, and dot predict the line, right? Linear regression dot predict the x. So this is what my y will look like, and let me color this as red. Okay, so basically I'm plotting x and y as a scatter plot. X and linear regression dot predict x. That means that the line of y, and the color of that line should be red. And let's just plot this title. So plt dot title. Title should be linear regression for crop yield, and in x label we have a fertilizer used, and y label we have plt dot y label. Sorry, not this. Y label we have corn yield, right? And we will plt dot show function to display the. Okay, so once I do this, I will see that my graph looks like this. Okay, so my data is varying in a polynomial fashion, and my linear regression line is this. So linear regression line will not be able to solve or predict anything in this data, right? Because my data points are not being touched by this linear regression line. All right, so quickly do this visualization. If you have achieved this graph, then type in done or yes in the chat box. Thank you so much, Shubham, Tushar, Jayesh, Ashwin, Lakshit. Thank you so much, Aryan, Harshvardhan. Thank you so much. Done. So you can see that the linear regression line is straight and it cannot fit this graph, right? Now we will visualize the linear regression results, polynomial regression results. Okay, so we'll copy this same thing. Nothing needs to be changed. We just need to change this. Now, instead of linear regression, we will be like poly regression, and we are going to predict it on X poly, right? So nothing has changed, just this code has changed. Instead of linear regression, we are now doing polynomial regression. Here also, we will change linear to polynomial. Okay. Polynomial regression for class topic. So we will use this polyreg object that we are using for polynomial regression, and we are going to predict it on X poly, right? And let's plot this graph. See, if we can plot this graph just by changing the features of X, we were able to use linear regression, but that linear regression graph looks like this. All right. So this now, because we have covered all the data points in this, so this graph now this graph perfectly fits the data, right? But it still is generalized. So if I talk about like overfitting, so let's change our variables now. So let's change the degree of our polynomial to 3, let's say. Okay, and run this code. So degree of polynomial is 3 now. Nothing will happen to this graph. But what happens to this graph is it becomes more steeper. Let's say, let's take the degree as 10. Okay. So degree of polynomial is 10 now. And you see that it now tries to, you know, fit each point in this. Okay. So as I increase the degree of polynomial, it tries to like either underfit or either overfit. So for our data, which is degrees 2, the fitting was almost perfect. So the data was almost perfect. Okay. So in this case, it is perfectly fitting. So our data was y equal to x squares data. So it was not in reality actual data. It was a morphed data which I created for this class only. That's why it for polynomial degree of 2, it is fitting perfectly. So some people are asking, why is it overfitting? So it is not, it is overfitting because I made this fabricated data. So this data was fabricated. So no data will be like y equal to x square, right? So it will, these data points would be in somewhat fashion like this. But because I doctored this data to fit it in a polynomial, that's why it is kind of like looking like it is overfitting, because for y equal to x square and for y for degree of 2, it will always like perfectly fit this. Okay. So the code is this for visualizing the polynomial regression class. And we can see that if we change the value of degree, so let's say I change the value of degree of polynomial to 40, and let's see how the curve behaves in this manner. So now it has deviated from the path. So if my data was something like this, then I could have used the degree of 40, and I could have also fit a curve which is not y equal to x square, but in somewhat in this crooked fashion. So it is very interesting. Now I can fit any curve that I have just by varying my degree of the polynomial. Okay. Code of the polynomial graph is here. So we needed to change just this. So x and instead of linear regression, we put polynomial regression and predicted it on the base of x poly, right? All right, those who have achieved both of the graph, please say yes or done. So there's an interesting question right now. How could we decide the degree of an unknown data? So we cannot decide the degree. It's always trial and error. So what we will do is we try and error with the degree of with this hyperparameter n, which is called hyperparameter tuning. So we tune this hyperparameter in order to fit that graph. So we will not be able to determine which degree of the data, which degree of polynomial should we use. We can only try and check again and again which graph is overfitting, which graph is underfitting, which graph is perfectly fitting, so that we tweak n and then fit any type of graph. All right. Okay, so Abhishek is saying that he is getting an error here, which is what is the error? Like I can't see the error. I can just see the code, right? So maybe x is capital here, and somewhere you are using small x. So maybe that's the error. Abhishek, your error can be of, let me just share the whole screen so that you can also see where x is capital, whereas it should be small. All right. So now what we will do is we will predict a new result with polynomial regression. That means that we will make a input all right, so let's predict a new result with linear regression. So let's say we predict y. We use this linear regression class, linear regression dot predict, and we predict this. Let's say if we use 6.5 kg of fertilizer, how much corn yield is there? So for 6.5 kg of fertilizer, it says that minus 33 is, sorry, I am using this. It should not be negative. Yeah, so it says that for 6.5, linear regression says that my yield should be negative, which is not desirable, right? Because my data for 6.5, it should not be negative. Like, how can I get a negative crop yield? So let's check it with polynomial regression. So polyreg, and let's polyreg.predict. Let's predict. Let me just short my degree first. So degree is 2. Otherwise, what it will do is it will predict different. So with degree 2, I predict it for, sorry, 6.5. So I am using this double brackets for two-dimensional array, and I see that x has one features, but oh yes, I need to transform that 6.5. I need to transform that using the PF, right? So I need to fit transform 6.5. So PF dot fit transform, because I have not extracted the features yet. So I need to extract the features also. So I extract features of 6.5, and then I will not have any error. So it predicts that 15 kgs of my crop yield should be there if I use 6.5 kgs of fertilizer. All right. So we could predict it with linear regression, and we were getting an error from linear regression, and with polynomial regression we got 15 kgs of data. Yeah. Sushant is saying that he is stuck at the polynomial regression and linear regression showcase. So I will just hide the output here so that you can see both the code here. And I will also delete this so that you can see both the code. This is for linear regression, this is for polynomial linear regression, and check where you are making a mistake. All right, so we have 20 more minutes and we will cover logistic regression today. So those who are having error or those who are stuck somewhere, I will take your questions and all after the 6 p.m. Okay. So let's get back to the car purchase problem. All right. So now we were having this this problem we were having yesterday, right? Whether a company, TIA, is making some car and it wants you to predict whether the customer will buy my car or not, right? So in case of linear regression, uh, the the y was varying linearly with x, right? But here a y has only two values, one for the person who has bought the car, or zero for the person who has not bought the car, right? So on the base of the values of age and the customer salary, we are predicting actually whether the person will buy the car, one, or whether the person will not buy the car, which is zero, right? So this type of problem is called a classification problem, and it is different than a regression problem where we are trying to predict a continuous value of y. Okay. I am not sharing the wrong screen, right screen. Thank you so much for letting me know. All right, so we were having this car purchase problem. So of the company Tia, and the company was making the car, and the company was asking you to predict whether the person will buy the car or not. But the output of the company was either the person buys a car, one, or either the person does not buy a car, zero, right? In case of any other regression, right? The regression that we did, the output was a continuous value. We were predicting some value, right? But in the case where we are trying to determine whether the person will buy a car or not, this problem becomes a classification problem. We are classifying the data into yes or no, whether the person will buy a car, yes, or whether the person will not buy a car, which is no, right? So the customer data has only two values of output, which is 1 and 0. And according to the customer age, we can determine whether the person will buy a car. Now, how to solve this problem? Can we fit a line? Like if we try to fit a linear regression problem, so if we have age of the person here and whether the person has purchased the car or not, so the data will look like this, right? So we need to make a decision whether the person will purchase the car or whether the person will not purchase the car. So if we try to do it with regression, we will not be able to fit a single line, right? So the regression method will not work, because in regression, we will try to predict the values of y other than zeros and ones also, right? Here the value is 0.2, here the value is 0.4, here the value is 0.6, but that does not uh, make a decision of whether the person is buying a car, one, or whether the person is not buying a car. So a function that fits this perfectly is called a sigmoid function. So if you are into mathematics or if you are into engineering, then you must know this function, which is called sigmoid function. And the sigmoid curve looks like this. So it starts 0 for lower values, and for higher values, it is always 1. Okay, so if we can somehow fit this sigmoid function into a linear regression, then we will be able to achieve this classification, right? For all the values which are here, it will predict 0. For all the values which are here, it will predict 1, right? So if we can make a sigmoid function. So the equation of a sigmoid function looks like this: y equals 1 upon 1 plus e to the power x. So for lesser values of x, this graph, this y value is around 0. So for lesser values of x, and for greater values of x, the value of this y is 1. Okay. So now what we will do is we will feature engineer our linear regression formula into this sigmoid function. So basically we will use linear regression only, but we will feature engineer this linear regression to fit in this sigmoid function formula. So what we will do is we will take this linear equation, linear regression equation, and in the place of x, we will put it here. Okay. So basically, we will predict y, and then we will model that y to behave like a sigmoid function. Okay. So I put that equation of y equals b0 plus b1x1 into this equation, and now the linear regression equation fits to behave a sigmoid function, which is y. Okay, so I map the linear regression to fit the sigmoid curve. All right, so I will explain it one more time. I have this sigmoid function, which looks like this. So I will try to predict y, and after predicting y, I will model it to behave like a sigmoid function. Okay. So basically that line that we are predicting here, I am basically feature engineering it for lesser values of y. I am saying that you have the value of 0, and for greater values of I am saying that the value is 1. Okay, so I'm changing this line to fit a sigmoid curve, and that's how I am achieving the linear regression. Okay, sorry, the logistic regression. This is called a logistic regression. So the curve is called a logistic curve. And if I see it in 3 dimensions, so if I have two variables like customer age and customer salary, which is there in the example, then I will have a 3 dimensional problem. So the y will be in this 3rd dimension. So these orange dots are basically the people who have not bought the car. They are at 0. And these blue dots are basically 1. So these blue dots are actually at y equal to 1. So they are coming out of this curve, and they are at 1 here, y equal to 1 here. Okay, so basically this is coming out. I cannot show it like a 2 dimensional in a 2 dimensional curve. Basically it is coming out of the screen. So basically a linear regression in 3 dimension will look like this. So in y-axis there will be two values, zeros and ones, and these blue dots are the people who purchased the car, and these orange dots are the people who did not buy the car, and these blue dots are actually coming out of the screen and they are not in the screen itself. Okay, so we will try to map a linear regression curve to fit this sigmoid curve. So for multiple linear regression, it will behave like this: b0 plus b1 x1 plus b2 x2, because this is the equation of a multiple linear regression. So I fit it into a sigmoid curve to do the logistic regression. Okay. Now in logistic regression, we have another term called decision boundary. So decision boundary is a boundary in our curve which separates the input and the output. So decision boundary, in this case, this line can be the decision boundary. The points which are at this side of this line are actually buying the car. The points which are at this side of line are not buying the car. So decision boundary separates the decisions of buying a car and not buying a car in the data. So it separates the categorical variable in the data. Okay, so decision boundary is also what we need to find when we are doing the logistic regression. So all the points which will lie here in this plane, they will buy the car. All the points which will lie here, they will not buy the car. Okay. So now if your data looks like this, so if you have a data where all the people who are inside this circle, they buy a car, and the people who are outside the circle, they don't buy a car. So in this, the decision boundary was a line. Okay. Here, the decision boundary is a curve, right? It's a circle. So how to achieve this circular decision boundary is what we have learned in polynomial regression. So what we will do is, instead of linear regression, we will change the features of X to behave it like a polynomial regression. And we will pass that polynomial regression to a sigmoid curve. And that sigmoid curve will define whether the person will buy a car or not, right? So in order to fit a non-linear curve, non-linear decision boundary. So this is a decision boundary. So that's why a linear regression will lead to a linear decision boundary. And if I do polynomial regression, that means I extract the features of X, I can also achieve a circular decision boundary. Okay, because the equation of circle is like this, right? X square plus y square equal to r square. So I can fit any type of curve, whether it is like this, whether it is like this, by changing the polynomial features here. So if I change the degree of polynomial, I will be able to fit any of the curve, and I will be able to do any classification of our data. Okay. Now let's code this. The template is here. I will just copy this again. So it's in the same folder, but different with a different name. So you go to, I'll just share the correct. So it's here. So you go to drive. Wait. So I'll share this link again, and let me check if the link is correct. So I'm copying this from here and I'm sharing it in the chat. Okay. So the link is here for the code. So we will just check it once. We will not code it today because we don't have time to code. So just the theory of how the linear regression is there. So I think it's a simple linear regression template. So not the simple linear regression. I think it should be polynomial regression and it should be here. Yes, classification, right? So we are doing classification. So tomorrow we will do support vector machine, k nearest neighbor and logistic regression classification. So logistic regression is what we were doing. So I will share this folder, but we will not do this today because it is getting so much heavy. We already have covered polynomial and multiple linear regression. So we will not be able to do this today. So logistic regression we have done. The theory part is being covered today. So tomorrow we will do. We will start directly from coding. We will cover logistic regression and we will cover k nearest neighbors, which is one more way of doing logistic regression, and then we will do support vector machine. And because KNN is very simple, so we will be able to cover this in 20 minutes. Support vector machine we will cover in 20 minutes. So 20, 20, 20, which will be 1 hour. And for 1 other hour, I will be exploring supervised, unsupervised learning and reinforcement learning. Okay. So I will just share the code, the link for you to download the data sets. We will not code it today. So we will just close with the theory. So the theory is that we were doing logistic regression, and logistic regression is where when we were making a decision whether the person will purchase the car or not, and we were trying to find a function which can estimate this kind of curve, and a sigmoid function was the best estimate of that curve, and we try to like feature the linear regression into this sigmoid curve so that we can fit the data. And if the inputs are more, then we fit a multiple linear regression. If the decision boundary is kind of like a curve, then we feature engineer the input to fit a polynomial regression, and we can obtain any kind of decision boundary. We will see it tomorrow when we will try to do the logistic regression on Python. All right, thank you so much. I will share the PPT with you. Yes, of course, I will share the PPT. I will also share the PPT of last 2 classes also, right? All right, so we thank you so much for those who have joined. The CSR box team is here for you. So they are also going to make an announcement. So please, Team CSR box, you can take up from here. I have finished. I will wait for the people, those who have any errors after 6 p.m. to 6:30. Wait for your attendance also. For today's attendance marking, you need to download the multiple linear regression IPYNB file. Okay. So you need to download the multiple linear regression IPYNB file and you have to upload that only. So no, not uploading the polynomial regression, upload the multiple linear regression file only. Okay. Yeah, CSR box team, you can take up from here.
Yes, Amit, thank you so much for the session, and I'm sure the students have definitely benefited from it. Just have 2 small announcements to make before Amit can clear all your doubts for you. One is that, yes, we will be sharing the attendance link right now in the chat box as well as the WhatsApp groups for those who are watching live. Please update your attendance for the day as well as upload the file.